Let us discuss this matter once again. The operation procedure. You see, we have gone through one YouTube video about it. The process is more or less same. First, our machine is supposed to be placed on a solid, a level surface itself. And it should be on a found solid base. Next, we have to provide power to the machine of the range 440 volt, 415 volts, or 415 volts, 3-phase and 50 milliwatt AC supply. Next, workpiece is supposed to be clamped on the both the ends to the vise provided on the machine itself. I have told you that the workpiece is in the form of dumbbell, where both the ends are squared in cross section, and in between the both the ends, the portion of the workpiece is round in shape. Now we have to know the length of the workpiece is equal to the length of this round shape portion of the workpiece, but not the square shape, because square shapes are supposed to be used and supposed to be placed inside this vice's square end of the vice itself. Now, after clamping the diameter of the workpiece in the round shape and calculating and measuring the length of the workpiece between the two dumbbell, now we clamp the workpiece inside the machine itself. First, left hand side vice is a stationary vice. It cannot be moved. You just put inside the workpiece and tighten the workpiece by means of the fixing bolt itself. And right side vice of the machine in front of the machine is supposed to rotate the workpiece, so it can be rotated either clockwise direction or as well as anti-clockwise direction. You can, by rotating anti-clockwise or clockwise direction as per requirement, you will just match the square size of the end of the workpiece to that of the vice, and put the vice closing the vice by moving the right portion of the machine towards the left portion of the machine. Thus, the work went inside the hole of the vice, and there you will clamp it by means of this fixing screw. Now, set the digital DOS portion to zero position. First we have to start. Next we have to put it to the 0, and you have to push the buttons at the written as peak, where peak is the because if you push the peak button, the display at the moment where this bar will be broken, remains in the display device. You don't go back to the 0 position. But if you don't push the peak button after the breaking of the bar, this deflection will go back. The torque will go back immediately to the initial 0 position, which we cannot we can record. So this is the most important part, to push the peak switch and push the 0 switch, which will bring the reading of the microprocessor digital device into the 0 position itself. Now, then start the machine, and then first, before starting the machine, you put this graduation of the vice to the 0 position, because the bright is graduated from 0 to 5 as a graduated scale fixed over it, which is graduated from 0 to 360 degree. First, you post it in the 0 degree, and then start the machine, rotate the workpiece or twist the workpiece in direction, so that the reading start from 0 to 360, not from 360 to 0 itself. Then continue the rotation and record the rotation as well as the record on the microprocessor based display device, to which will give out the torque which is generated as per with the twist of the material itself. We will find that after the torque is not increasing after a certain value, which remains more or less there until the torque breaks the material, until the vice breaks the material itself. Then we have to workpiece the vice breaks, then plot the torque and twist curve itself. Twist curve will be given the readings in degree, and torque will be the readings given in the device itself. Plot a torque and twist curve itself and read the coordinates of the coordinate convergence point from the straight line portion of the torque twist curve and calculate the value of z using the relation itself. So the torque twist curve will increase to a certain extent, and after it will become straight and more or less parallel to the twist, parallel to the torque line itself. Thus, torque is stable up to a certain extent after the current is under the twist. The value of twist will be obtained from your reading itself when the bar breaks the material itself. When the machine is not in your let us go through another few videos here.
All right, so here's Dave, and he's going to demonstrate the aluminum torsion test, or perhaps the pencil torsion test. What's he doing here? He's using the pencil as a straight edge, and he's drawing this handy black line with the Sharpie on the torsion specimen. And you can see here again, it's the same specimen, a dog bone with the flats milled onto the ends. Now it's time to actually load a specimen into the actual chuck. For those who have your green pass, you're familiar with the spring-loaded chuck key, right? And the reason they're spring-loaded is that you can't accidentally leave the handle in the chuck, and then it starts spinning at a couple thousand RPMs, potentially killing people. This, as you'll see, does not spin at a couple thousand RPMs, closer to less than 1 RPM, but nonetheless we have the spring-loaded chuck just to be safe. Now he's trying to get the flats, the flats on the specimen aligned with the jaws in the chuck with one hand, and with the other hand valiantly attempting to use the spring-loaded, the safety key. Now he's given up, and he's going to just use both hands to tighten that chuck, and hopefully it kind of wiggles and wobbles its way to be nicely aligned. And so he's got that in there. Looks pretty good, Dave. Yeah. Now he can tighten it all the way down. And you can see how the spring kind of pushed it out of there. So now remember that this is free to slide, and so he's got to open that side. We'll talk a little bit about why it needs to be free to slide. You can see maybe by dumb luck he came pretty close to having the flats and the jaws aligned. Maybe not quite, so it looks like he'll have to jog the torsion side, the motor side, that one right there. So he'll use that, he'll turn the right side so that the flats on the left side align with the jaws on the left side. Now keep in mind that this one does not twist. Well, it does twist a tiny bit, and that's what allows the torsion cell to read, but it's really imperceptible. Tiny fractions of a degree. I don't think it even rotates a hundredth of a degree. So effectively the left side is fixed there. The blue thing is the torsion cell. And so that jaw is fixed. Now it's important that this thing is free to slide. We do have the capability to tighten it down, but we don't. So he's just going to slide it over. It lines up right with the flats. Very good. And so now he'll use the key again on this side to tighten it down. The reason we let this thing slide is that we want to test this thing in torsion, and I know that you have all learned that torsion generates a shear stress, or torsion results in a shear stress. But as we twist this thing, imagine it's a bundle of fibers. Oftentimes we imagine even amorphous or isotropic materials to be a bundle of fibers. As we twist it, it gets shorter, and we want to allow it to shorten. And otherwise we'd impart a tensile load on it as we twist it. So it's important that that left end can slide. Okay, so he goes over here. and just put clicks or zeros the two channels there. You don't have to right click it. There's actually a little button for zeroing, and then he clicks play and it begins. And what's going on? This makes no sense. We've got angle and torque, right? Angle on the horizontal axis, torque on the vertical axis, but the torque is dropping. Yeah, so it turns out that with this one, as we're looking into the chuck, a counterclockwise torque is considered negative in this case, right? Not a big deal. We can handle that. And you can see this thing is rotating at, almost one full revolution per minute. So it's pretty high strain rate as this thing twists. And if you look down there, I can barely read that. It looks like we've hit 200 degrees of twist already in just under a minute, so that about makes sense. And we can see that it's already starting to level off. There's very high resistance to the rotation at first, and then it drops off, right? As you've learned in 303 or 306, that the torsional shear stress is not evenly distributed. It starts on the outside and it works its way inward, which means it's highest on the outside, which means the first place it starts to yield is on the outside. Okay, so now we've spun over one full rotation. You can see that black line that Dave drew on the specimen. We can see there's one full wrap of that black line now. So that black line really gives us in my opinion, a much more visual clue, or a better way to see how fast this thing is rotating and how much it's rotated. So now we're up to, I can't quite read that, for 600 degrees, 800 degrees, something like that. So we're about 2 revolutions, almost 2 revolutions, and we can see that there's almost 2 instances of the line. We're kind of making a candy cane barber pole kind of thing out of the specimen, and so we again can see right now the strain, the angle of twist seems to be pretty evenly distributed as this thing rotates. You'll learn a lot more about the relationship between shear stresses and normal stresses a little later this semester, but we wanted to show you how to use this equipment. For those who want to use it for their project, can. Now we're just starting to see that second black line show up on the right end there, and we're approaching 800 degrees, and the torsion is very much leveled off. Now this indicates to us that all of the material is now yielding, right? Remember the torsional shear stress is highest at the surface and lowest at the center. Once the torque has totally leveled off, we can assume that all the material, all the aluminum is yielding at this point. There's 2 ways to determine the yield stress. We won't be doing it because you guys don't quite have the information you need from 303 or 306. But the first place to identify yielding is when it becomes nonlinear at about, it looks like maybe about 30 or 50 degrees of twist there. The other way to do it is by looking at once it's all yield, or what is its maximum sustained torque. And now we can see it's the shear stress, or the deformation angle of twist. It appears to be, maybe not quite as evenly distributed anymore. It looks like the lines on the right end of the specimen in the upper right corner there are kind of bunched up there. If this was a perfect world, the shear stress would be, or the angle of twist would be evenly distributed. But the fact that now it's definitely bunching up on the right end, you can see that the 2 right lines are very close together. So it's twisting more on the right end. Why is that? There might be some cracks forming. There might be some locations on the surface where we have achieved the ultimate shear stress, and it's beginning to fail. So if I were a betting man, which I'm not, I would bet that it's going to fail on the right end, just because that's where all the deformation is starting to happen. Oh, what's going on here, Deb? Yeah, he's maybe observing that it's the right end seems to be twisting a lot more, and it's twisting more Yeah, the universal silent movie sign for this is hot. And so, oh, look at that. Sure enough, it fractured on the right end, and our load dropped or went up to 0, which means this has failed. So they click stop. This doesn't stop automatically like the tensile and compression methods. This would just keep going until we stop it. And now we've got to get that specimen out of there. We got a little problem. Why is he jogging it? Yeah, because there's no place to put the key. So he's got to jog that torsion head all the way around. Yeah, you still can't see it. Now he slides that thing away. It did shorten considerably. So now you can jog it. There's a high-speed jog and a low-speed jog on this thing. He's going to use the high-speed jog, jog it around until he has access to that square keyhole. And then he'll use, of course, the spring-loaded safety key to loosen that thing up, and he can get the specimen out of there. You can see the spring there. Very important to use a spring-loaded one in the machine shop, a little less important here. So there's the short end, the proverbial short end of the stick, and you can loosen up that end. This is very interesting. If you recall the tension experiment, or at least the video of the tension experiment, the fracture surface, oh, still hot, yep, still hot. The fracture surface was 45 degrees. In this one, the fracture surface is totally normal to the axis of the specimen, right? So it's a perpendicular, normal. And it fractured on that surface for some reason. Again, you'll learn more about that later on this semester in 303 or 306. And you'll learn much more about that when you take machine, for those of you mechanical engineers or BSEs, when you take machine component design. All right, now we got to save our data. A little quirky here. We're going to save the test data with the save icon. It's got this long file extension, mtw data, the world's longest file extension. Dave is just going to eliminate that. And he's just going to give it some informative name, online torsion data aluminum. He clicks OK. So what it has done now, it has saved the data in a proprietary admet format. And so he's going to go down here and save it in the 307 folder. There it is. Okay, but now he needs to export it, right? We're not too interested in proprietary file formats, so we're going to export it as a comma-separated variable. He's going to put that somewhere intelligent. Looks like on the desktop in the 307 folder. It's always fun for me to look at this folder because it's kind of a little tour of TAs past, right? There's some legendary TAs on this list here. But Dave is now first making his mark, so he makes his own folder. He's going to export the comma-separated variable file into there. So now we have it in something that we can read with MATLAB or Ease or Excel, Google Sheets, whatever. It takes a little while to do. And not quite enough time to play the girl from Ipanema here. But okay, so it's done. I'm saving. Dave, being the cautious and conservative engineer that he is, he's going to open up the desktop and just make sure that that data file looks the way it should. Double click on that. Okay, so now you can see that there's a time, a torque, and an angle channel that all show up, and then a bunch of other stuff that says NAN, N-A-N. That's kind of mathematical speak for, or computational numerics speaks for not a number. Thank you, Dave.
Hello respected teachers and my dear friends. I came forward to introduce torsion test. What is meant by torsion test? Where it is applicable? Why we want to do torsion test? What is the desired outcomes while doing torsion test? So guys, I would like to explain these all things. Initially, what is meant by torsion? Torsion means twisting. For example, if you are applying a force to a manual screwdriver, you are applying torsion. Similarly, a rod being turned by a mechanism around its longitudinal axis is experiencing a torsion force. So, guys, you might have observed what I am reading. So, torsion means when we applying force to a material, it is nothing but torsion. Torsion, another name called as twisting force. Twisting force in the rotational motion, we have to say twisting force is nothing but torque. So torsion test comes under destructive test. It is nothing but specimen achieves breaking or failure point. It means testers testing the material or specimen until the failure or breaking point. It is called as destructive test. So we have so many destructive tests. So for example, tensile test, compression test, impact test, torsion test, these all are examples comes under destructive test. So friends, I would like to explain torsion test. That is, torsion test twist a material or test component to a specified degree with a specified force or until the material fails in torsion. It means, guys, in the torsion test here we see the diagram. A material can be twisted both sides, but in the torsion test we have only one movement to twist the material. So I will explain the process of the torsion test, procedure of the torsion test later. I will explain. So what is our aim means to find the from the torsion test we have to find the rigidity modulus by using torsion test or by using torsion test machine. So rigidity modulus is a mechanical property. It is nothing but the ratio of shear stress and shear strain. When we doing twisting movement, stresses are developed. Or when we doing twisting movement, cross section will be changed. That is nothing but shear strain, and stresses are developed. That is nothing but shear stress. So rigidity modulus is equal to the ratio of shear stress by shear strain. So we have to take apparatus, torsion test machine, vernier calipers, and one specimen. Initially, we have to take dimensions of the specimen for calculating rigidity modulus. So we have one equation, that is T by J is equal to tau by R is equal to G theta by L. G is equal to T by L by J theta. So T stands for maximum twisting force, how much we are applying force. So by using torque meter, we know that J stands for polar moment of inertia is equal to pi d power 4 by 32. G stands for modulus of rigidity. It is a finding factor. L stands for length of the shaft and nothing but gauge length. From this diagram, friends, I will show you how to take the gauge length. This is a gauge length. We have to take this length for gauge length, and these three sections we have to take diameter with the help of vernier calipers. By using this with the help of this diameter, we have to calculate polar moment of inertia. So what is polar moment of inertia? It is equal to pi d power 4 by 32. So about these three sections, we have to average these three sections, we get one diameter. With the diameter we use with the diameter we have to calculate polar moment of inertia. How to do torsion test? So friends, fix the gauge length on the shaft with punch marks. Measure the diameter of the shaft at three sections with the gauge length with the help of calipers, vernier calipers, and take the average value for calculating polar moment of inertia. From the expression, T by J is equal to tau by R, where tau is shear force, R is radius of shaft cross section. Find the permissible torque that can be applied on the shaft for the assumed permissible shear force. Now select the suitable range for the torsion test machine. Fix the specimen. Apply the torque slowly by rotating the handle to the right side of the machine. Now the torque from torque meter and corresponding angle of twist from angle measure disc. Repeat the experiment twice and thrice. Take the 6 readings. We have to know by doing average these all things. We have to calculate the rigidity modulus. So how to find the rigidity modulus, friends? We will go to the back. That is we have one equation, that is tau T by J is equal to tau by R is equal to G theta by L. So G is a finding factor. So T means torque, maximum twisting force. So we have two machines, guys. In the laboratory we have two machines. So one machine have 0.01 division and another machine have 0.05 division. So your wish, which your wish, you will go which is comfort, which is easy to calculate. So each 5 degree we have to take the reading. So T is a torque and J is a polar moment of inertia. About 3 sections we have to take average diameter. The diameter with the help of diameter we have to calculate the polar moment of inertia, that is P pi d power 4 by 32. So next thing, R is a radius. So G is a finding factor, theta is the angle of twist, L is a gauge. I will show you tabular column how to take readings. So initially we have twisting moment, another one is angle of twist, another thing finding factor, that is modulus of rigidity. So initially I take 34.5 kgs, that will convert it into Newton meter. So we have to calculate 9.8, so we get Newton meter. So another thing is angle of twist. Each 3 degree angle we have to calculate how much we are applying load. So that 3 degree angle converted into 0.052, that is radians, in terms of radians. So from these two things and one of the polar moment of inertia 430.8. So diameter of the shaft is 88.14 and gauge length is 15.2. So these all things so put into this formula, that is tau by J, T by J is equal to G theta by L, so is equal to tau by R. So finally we get rigidity of the modulus. So friends, so by this video I hope that you are understanding very well. So this is a torsion machine. This is a torque meter. So here we have angle of twist. So this point to this point we keep specimen. So finally my conclusion is that so torsion is nothing but twisting moment. So it is a very simply test from the destructive test. So I think you might have observed everything. So you like it, you can subscribe this video.
नमस्कार दोस्तों, मैं प्रकाश कुमार सैनी। मैं आज आपको बता रहा हूं दोस्तों टोर्सन टेस्टिंग मशीन। ये हमारे पास टोर्सन टेस्टिंग मशीन है। इसके ऊपर कौन कौन से इंपॉर्टेंट पार्ट्स लगे, उन सब का क्या काम रहता है और टोर्सन क्या निकालते हैं। दोस्तों टोर्सन क्या रहता है, किसी भी मटेरियल की मैक्सिमम शेयर स्ट्रेंथ निकालने के लिए इस टोर्सन टेस्टिंग मशीन का यूज किया जाता है। यानी किसी भी चीज़ को घुमाने पर कितना ट्विस्ट लग रहा है, कितना फोर्स लग रहा है, कितना टॉर्क लग रहा है, उसको निकालने के लिए इस टोर्सन टेस्टिंग मशीन का यूज किया जाता है। तो सबसे पहले टोर्सन टेस्टिंग मशीन है, उसके ऊपर इंपॉर्टेंट कौन कौन से पार्ट्स लगे, उन सबका क्या काम रहता है। तो सबसे पहले दोस्तों ये नीचे वाला होता है, ये बेस होता है। बेस के ऊपर ही सारे पार्ट्स फिट कर दिया जाता है। ये क्या करते हैं, पूरा कास्टिंग करके बना दिया जाता है। तो ये बेस होता है। इसके ऊपर ये हॉरिजॉन्टल बीम रहता है, उस बीम के ऊपर जो मोटर लगी रहती है वो मूव करती है। ये मोमेंटम एरिया रहता है, मूव करती है, इधर से उधर मूव करती है हॉरिजॉन्टल पोजीशन पर। और ये वाला एरिया रहता है, ये वाला फिक्स रहता है। ये इसके ऊपर लोड अप्लाई करते हैं, तो लोड अप्लाई करते हैं तो लोड कहाँ दिखाया जाता है, ये डिजिटल लोड इंडिकेटर इसके ऊपर लगा दिया जाता है। अब ये इसके ऊपर जो मोमेंटम की तरफ रहता है, इसके ऊपर मोटर फिक्स रहती है। मोटर के ऊपर एक ये डिस्क फिक्स रहती है। इस डिस्क के ऊपर 360 डिग्री का एक एंगल प्लेट लगी रहती है। उस 360 डिग्री वाले एंगल प्लेट से हम देख सकते हैं कि इसके अंदर कितना ट्विस्ट करने पर कितना लोड अप्लाई हो रहा है, और ज़्यादा ट्विस्ट करने पर कितना ज़्यादा लोड अप्लाई हो रहा है। तो ये हम मैक्सिमम शेयर स्ट्रेस इस तरीके से निकालते हैं, ठीक है ना। मॉडुलो और रेजिडिसी किस तरीके से निकालते हैं। तो सबसे पहले ये मूवेबल पार्ट होता है, ये फिक्स पार्ट होता है। इसके ऊपर डिस्क के ऊपर हर एक एंगल लगाए, 0 से लेके 45, 90 यानी 360 डिग्री का एंगल इसके अंदर फिट किया है। जब ये डिस्क मूव करती है इस तरीके से, जब हम इसको चलाते हैं, ये चलाने पर ये क्या कर रही है, मूव कर रही है इस तरीके से। ये मूव कर रही है तो ये कितने डिग्री पर कर रही है, हम क्या करेंगे, अभी ये 0 डिग्री है, फिर 90 डिग्री पे इसकी रीडिंग लेंगे, फिर 180 डिग्री पर लेंगे, 270 डिग्री पर लेंगे, और फिर 360 डिग्री पर एंगल पर रीडिंग लेते हैं। इसके बाद एक बार पूरा रोटेशन हो गया, दूसरे बार रोटेशन हो जाता है, तो फिर हम एंगल को इसके साथ ऐड करते चले जाएंगे। 45 हो गया, फिर 90 हो गया, तो इसका हम ऐड करते चले जाएंगे, और कितने लोड पर कितने एंगल पर ये शेयर स्ट्रेस प्राप्त होता है, तो हम इसके बारे में आप बताऊंगा, ठीक है। मैं इसको फिट करके बताऊंगा। तो इस तरीके से ये पार्ट्स होगा, नीचे वाला बेस होगा, ये हॉरिजॉन्टल बेस होगा, ये मूवेबल पार्ट हो जाता है, ये फिक्स पार्ट हो जाता है। इस तरीके से ये टॉर्सन टेस्टिंग मशीन के पार्ट्स रहते हैं। अब मैं इसको फिट करके बताऊंगा किस तरीके से ये पार्ट्स को फिट करते हैं और मूव कराते हैं। तो ये हमारे पास 2 वर्क पीस रखे हैं। ये वर्क पीस रहता है दोस्तों इसका, इस पर क्या रहता है, ये इसका जो रेक्टेंगल शेप रहता है वो 16 mm का रहता है, और इसके अंदर की जो गेज लेंथ रहती है 110 mm के लगभग इसकी गेज लेंथ रहती है। और इसके ऊपर जो डायमीटर जो बनाते हैं, लेथ मशीन से बनाते हैं, वो 15 mm का डायमीटर बनाते हैं। अब मैं इसके बारे में आपको अगले वीडियो में इसके बारे में आपको बताऊंगा किस तरीके से एक्चुअल रीडिंग किस तरीके से ली जाती है। आज मैं आपको बेसिक बता रहा हूँ। तो सबसे पहले इस वर्क पीस को हम लगाएंगे। वर्क पीस को लगाने के बाद कितना ट्विस्ट होता है, कितने लोड पर ट्विस्ट होता है, उसके बारे में आज आपको पूरा समझाऊंगा। तो मैं इसको फिट करता हूँ पहले, इसके बाद मैं आपको इसको ट्विस्ट करके बताऊंगा किस तरीके से ये ट्विस्टिंग होता है। तो इसको अच्छे से तरीके से फिट कर लेना चाहिए, और एलन की वाले बोल्ट से इसको टाइट कर देना चाहिए। इसको मैं आपको बिल्कुल पास के ला के बताऊंगा किस तरीके से ये ट्विस्ट होता है और ये मूव करता है। थोड़ा सा मैं आपको समझाता हूँ। ये डिस्क है, देखो इसके ऊपर अलग अलग एंगल बने हुए हैं, 0, 250, 240, इस तरीके से ये मूवेबल रहता है, ये फिक्स रहता है। तो ये मैं आपको इसको चालू करके बताऊंगा किस तरीके से इसके ऊपर ट्विस्टिंग एफर्ट लगता है, और फिर यहाँ पर से कितना लोड आता है, ये लोड भी दिखा दूंगा, ट्विस्ट करके भी बताऊंगा। इसके बाद मैं अगले वीडियो में आपको एक्चुअल रीडिंग लेके दिखाऊंगा किस तरीके से एक्चुअल रीडिंग लेते हैं। देखना इसके ऊपर कितना लोड अप्लाई होगा। जैसे ये टूट जाएगा वैसे ये रुक जाएगा। तो हम क्या करते हैं, हर 45 मिनट 90 ये तो इससे रीडिंग ले लेते हैं। तो आज मैं रीडिंग लेने में बता रहा हूँ आपको, ओनली ट्विस्ट करके बता रहा हूँ किस तरीके से ट्विस्ट होता है और इसके ऊपर किस तरीके से शेप बनता है। उधर लोड भी चल रहा है 42, 43, इस तरीके से इसका एंगल आ गया है 200, 210 एंगल। किस तरीके से घूम रहा है, एक तरफ फिक्स रहता है, एक तरफ से रोटेट रहता है, तो लोड उसके ऊपर अप्लाई हो रहा है। 52 हो गया, इस तरीके से इसका एंगल हो गया 370, इस तरीके से दोबारा रोटेशन होने लगा इसके ऊपर। इस तरीके से किसी भी मटेरियल का हम टेस्ट कर सकते हैं, टॉर्क निकाल सकते हैं, उसके अंदर कितने मैक्सिमम शेयर स्ट्रेस निकाल सकते हैं। इस तरीके से टॉर्सन मशीन पर किस तरीके से शेयर स्ट्रेस निकाल सकते हैं, तो आज मैं आपको बता रहा हूँ। तो देखो ये टूट गया है, टूटने के बाद इस